Every bridge in America stands on something you can't see: wooden piles, tree trunks pounded 40 feet straight down into riverbeds, into mud, into solid rock. In the 1800s, before concrete foundations, this was how you built a bridge. You took a tree trunk, sharpened the end, stood it upright, and hit it. Again and again. The machine that did the hitting weighed 2 tons and dropped from 40 feet. The sound could be heard for miles. Men worked underneath these machines. They guided the piles into position with their hands, while a cast iron weight the size of a carriage hung directly over their heads. One slip, one miscommunication, one broken chain, and that weight would drop, not onto the pile, onto them. This is the story of the steam pile driver, the machine that hammered America's infrastructure into existence. One blow at a time. To understand what pile drivers actually did, you have to understand what holds up a bridge. Not the cables, not the trusses, not even the stone towers you can see rising from the water. Those are just the parts above the surface. The real engineering is underneath. Every bridge needs foundations. Something solid to push against. Something that won't move when 10,000 tons of iron and traffic press down on it. And in the 1800s, finding that solid ground was the problem. Rivers don't have convenient rock shelves sitting 6 feet below the waterline. They have mud, silt, gravel, layers of sediment deposited over thousands of years, soft, shifting, unreliable ground that would swallow any stone you tried to set on top of it. If you tried to build a stone pier directly on river mud, here's what would happen. At first, nothing. The pier would seem solid, but over weeks and months it would begin to sink. Not evenly. One corner would drop faster than the others. The pier would tilt, cracks would form, and eventually the whole structure would fail. Engineers in the ancient world discovered this through painful trial and error. Bridges collapsed, temples settled and cracked. Entire buildings had to be abandoned because their foundations couldn't hold. So engineers did something counterintuitive. Instead of trying to remove all that bad ground, they drove through it. They took tree trunks, usually white oak or southern yellow pine, sometimes 40 or 50 feet long, sharpened one end to a point, and pounded them down into the earth until they hit something that wouldn't give. The principle is ancient. Until the Romans drove wooden piles for their bridges across the Rhine, Julius Caesar himself described pile driving in his account of the Gallic Wars. The Venetians built their entire city on millions of wooden stakes hammered into lagoon mud. Engineers in the 1800s weren't inventing a new idea. They were trying to do an old idea faster. Because here's the problem. Driving a single pile by hand took hours. You'd rig up a wooden frame, hoist a heavy weight on ropes, have a crew of men pull the ropes to raise it, then let it drop, over and over. Maybe 50 or 60 blows before the pile sank a foot. And a single bridge pier might need 200 piles clustered together in a tight grid. Do the math. 200 piles, 8 hours each. That's 1,600 man-hours just for one pier. One pier out of maybe 10 or 20 for a single bridge. And America, in the 1840s, needed thousands of bridges. The railroads were coming, and they could not wait for piles to be driven by hand. The first railroads ran on level ground. They followed river valleys where the terrain was flat and the grades were gentle. Steam locomotives of that era couldn't climb steep hills. They needed long, gentle slopes. And the gentlest terrain in America ran alongside rivers. But those river valleys had rivers in them, and rivers needed bridges. The problem was scale. A canal might cross a river at 1 or 2 points along its entire length. A railroad crossed whenever the tracks demanded. A line running parallel to a river might need to cross tributaries every few miles. Each crossing needed a bridge. Each bridge needed foundations. By 1840, the eastern railroads had burned through the easy routes. To expand west, they had to cross the Connecticut, the Hudson, the Susquehanna, the Potomac, the Ohio. These weren't streams you could ford. They were wide, deep, fast-moving waterways with soft bottoms and unpredictable currents, and every one of them needed a bridge built on piles. The demand created the machine. Sometime in the late 1830s, probably in New England, somebody connected a pile driver to a steam engine. The records are unclear on exactly who did it first. Several inventors filed patents around the same time. James Nasmyth in England developed a steam hammer for metalworking that influenced piledriver design. American mechanics adapted and improved these concepts. By 1845, the steam piledriver was standard equipment on major construction sites, and it changed everything. If you've never seen a piledriver work, let me paint the picture. Imagine a wooden frame, maybe 30 or 40 feet tall, built like an elongated A-frame or a tall ladder stood on end. Two parallel wooden beams running straight up, held together by crosspieces. At the top, a pulley system. At the bottom, a steam engine bolted to a heavy timber platform. Between those parallel beams runs a channel just wide enough for a massive iron weight to slide up and down. This weight, called the hammer or the ram, might weigh 1,500 pounds. Some of the bigger machines used hammers weighing 3,000 pounds or more. The largest pile drivers built for major bridge projects hoisted hammers of 4,000 pounds. The steam engine connects to the pulley system through a series of drums and cables. When the operator opens the valve, steam pressure lifts the hammer up the channel, 20 or 30 or 40 feet into the air. The operator watches. He times the lift. He knows exactly when the hammer reaches the top of its travel. Then he trips the release, and the hammer falls. No brakes, no cushioning. Just raw gravity accelerating 2 tons of iron through 40 feet of empty air. The mathematics are simple. A 2,000-pound weight falling 40 feet impacts with a force of roughly 80,000 foot-pounds. That's enough energy to drive a wooden pile several inches into compacted soil with a single blow. In soft mud, a pile might sink a foot or more. The sound cannot be adequately described to anyone who hasn't heard heavy equipment in operation. Imagine a cannon shot, but lower, with more bass. A sound you feel in your chest before you hear it with your ears. Windows rattled in buildings a quarter-mile away from construction sites. Horses panicked. People came out of their homes to see what was happening. The pile, this 40-foot tree trunk standing vertically in a guide frame, sinks maybe 6 inches into the mud. Sometimes more in soft ground, sometimes just an inch or two if it's hitting clay or gravel. Then the steam engine hisses, the cables tighten, and the hammer rises again. A good steam pile driver could deliver 40 to 60 blows per hour. What took a hand crew all day, the machine could do in 30 minutes. A single pile that might have required 8 hours of backbreaking manual labor could be driven in an hour or less. This was the multiplication factor that made the railroad expansion possible. Not just faster, orders of magnitude faster. But faster came with costs. The men who operated these machines worked in conditions that would be considered insane by modern standards. The pile driver had to be positioned directly over where the pile would go. On land, that meant building a temporary wooden frame and moving the whole apparatus on rollers or skids. Some pile drivers weighed 20 tons or more. Moving them was a major undertaking, even with horse teams. On water, that meant working from floating barges or temporary cofferdams. The barge would rise and fall with the current. The pile driver frame would sway. The hammer would swing slightly as it rose, adding unpredictable forces to an already dangerous operation. The pile itself had to be guided into position by hand. Someone had to stand at the base of the driver, wrestling a 40-foot tree trunk into the exact spot where it needed to go. The pile was heavy, unbalanced, slippery with sap or river water. It wanted to fall. It wanted to spin. It wanted to crush the men trying to control it. And directly above them hung several tons of iron, ready to drop. The hammer operators couldn't always see the men working below. The steam engine and boiler might be positioned to block the operator's view of the pile base. The frame itself created blind spots. Workers below relied on signals, a shout, a whistle, a hand gesture. In the noise and steam and chaos of a construction site, signals got missed. When the hammer fell on a pile that wasn't seated properly, the pile could kick out sideways like a giant spear. I've read accounts of piles shooting horizontally at lethal speed. Men were impaled. They were crushed between timbers. They were knocked off platforms into rivers and drowned. When the hammer fell while men were still adjusting the pile, the results were unsurvivable. A 2-ton weight dropping onto a human body leaves nothing recognizable. The accident reports from 1850s railroad construction, the ones that exist at all, describe injuries using clinical language that barely hints at the horror. Crushed? Struck? Killed instantly. And nobody kept accurate counts. These were Irish immigrants mostly, German laborers, black freemen, and escaped slaves, people whose deaths weren't considered important enough to record in detail. Coroners in rural counties didn't investigate industrial accidents the way they investigated murders. If a company doctor noted the death, that was considered sufficient. We know from scattered newspaper reports that men died. A brief mention in a local paper. A laborer was killed yesterday at the bridge construction site. No name, no details, just an acknowledgement that it happened and work continued. We know from company records that work stopped for injuries and resumed the same day. The log might note, delay of 2 hours due to accident, without specifying what kind of accident or who was hurt. We know from the memoirs of engineers that pile driving was considered one of the most dangerous jobs on any bridge project. These engineers wrote admiringly of the men who did the work, but they wrote from a distance. They didn't name the dead. The names of the dead are largely lost. What we have instead are the bridges, the piles driven, the timetables met, the railroads opened on schedule, progress measured in wood and iron, the human cost measured in nothing at all. If you're finding this useful, hit subscribe. I cover stories like this every week, the machines and the men that built this country. Now let's talk about how these pile drivers actually got where they needed to go. Driving piles for a railroad bridge wasn't like construction on dry land. You couldn't just set up your machine on solid ground and get to work. The piles needed to go into riverbeds, into tidal flats, into places where there was no ground to stand on at all. So the pile drivers had to float. The floating pile driver was one of the most remarkable pieces of construction equipment in 19th century America. Engineers would build a heavy timber barge, maybe 60 feet long and 20 feet wide, with enough freeboard to stay stable in river currents. The hulls were flat bottom for shallow water work, but heavy enough to resist capsizing under the weight of the equipment. Then they'd mount the pile driver frame directly on the deck. The steam engine and boiler went at one end, coal or wood storage nearby. The frame itself, that 30 or 40-foot tower, rose from the center of the barge. The whole thing looked top-heavy, and it was. Stability came from careful ballasting and the tension of anchor lines. The whole apparatus could be towed into position by steam tugs or rowed by work crews. Anchors held it in place against the current. 3 or 4 anchors, sometimes more, each one dropped from a small boat and set in the riverbed. The anchor lines ran to winches on the barge deck. By adjusting the lines, the crew could position the pile driver with surprising precision. The operator would fire up the boiler, wait for steam pressure to build, lift the hammer, position a pile, and start driving while the entire platform rocked gently in the water. Picture that, a 2-ton hammer falling 40 feet onto a pile that's being held by men standing on a deck that's moving with the river. The coordination required was extraordinary. Every person on the barge had to understand their role. One man watching the anchor lines for slack, another monitoring the boiler pressure, others wrestling the pile into position, the operator timing the hammer drops to avoid the worst of the barge's motion. The potential for disaster was constant, and they did this in winter. Rivers in the Northeast freeze. Not solid, necessarily, but enough to make water work dangerous. Ice flows could crush a barge, and a particularly cold stretch might freeze the barge into the river, trapping it until spring. The motion of ice against the hull created constant stress on the anchor lines. Frozen decks became slick with frost. Men wore hobnailed boots for traction, but wet wood with a layer of ice defeated any boot. Falls were common. A fall on a moving barge could send a man over the side. The water temperature in a New England river in January might be 33 degrees. A man in the water had minutes before hypothermia made swimming impossible. Men's hands, wet from handling piles pulled from the river, stuck to cold iron and tore skin off when they pulled away. I've read accounts of men whose palms were permanently scarred from contact with frozen equipment. They learned to work with gloves when possible, but some tasks required bare hands for grip and sensitivity. But winter was often the preferred time for pile driving. The water levels were lower, the currents were slower, and the frozen ground at the riverbanks provided stable staging areas for material delivery. Summer floods could raise river levels 10 or 20 feet in a matter of days. A barge positioned for low water might find itself in a completely different situation after heavy rains upstream. Winter was more predictable, brutal but predictable. So the work continued through December, January, February. Men in wool coats and leather boots, handling timber in sub-zero temperatures, working around a machine that required constant attention to steam pressure and cable tension. One contemporary account describes workers' beards freezing to their chests from condensed steam. The steam, billowing from the engine, would condense in the cold air, settle on their faces and clothing, and freeze. Men had to break ice off their coats during brief rest periods. Another account mentions men whose hands were so cold they couldn't feel when they'd been injured. A splinter driven deep into a palm, a finger crushed between timbers. They only discovered the damage when they took off their gloves at the end of the day and saw the blood. The piles themselves presented their own challenges. These weren't milled lumber products. They were whole tree trunks, bark stripped, ends sharpened, sometimes iron shod at the tip to help them penetrate gravel or hard clay. A single pile might weigh several thousand pounds. A 40-foot white oak pile in good condition could weigh 3 or 4 tons. Getting them to the construction site required log drives down rivers, loading onto barges, or hauling by wagon over impossible roads. A single wagon might carry 2 or 3 piles at most. A major bridge project needed hundreds. The logistics of material delivery consumed as much planning as the actual construction. Once on site, piles had to be lifted vertical and guided into the pile driver frame. This was done with rope and rigging, with men hauling on lines while others used pike poles to guide the rising timber. The pile started horizontal, floating in the water or resting on the deck. Workers would attach ropes near the top, run them through pulleys on the frame, and haul the pile upright. All of this by hand, with primitive rigging, by men who were learning on the job. The sharpening alone was a trade. A good pile point had to be symmetrical, or the pile would veer off course as it was driven. It had to be steep enough to penetrate, but not so sharp that it would split when it hit an obstacle. A 4-sided point was standard. Axes would rough out the shape, then adzes would smooth it. The final product looked something like a blunt pencil tip, maybe 18 inches of taper leading to a point or a small flat. Iron shoes could be fitted over the point for driving through gravel or rocky soil. Experienced sharpeners could shape a point in an hour. Novices might take half a day and produce something useless. A crooked point would drive a crooked pile. A weak point would shatter on impact. Getting this right mattered. Every pile driven represented dozens of hands doing jobs that no longer exist. The woodcutters who felled the trees, the teamsters who hauled them, the bargemen who floated them to site, the sharpeners who shaped the points, the riggers who hoisted them vertical, the spotters who guided them into position, the operators who worked the steam controls, the firemen who kept the boiler fed. A single pile, driven in maybe an hour, the product of an industrial system that stretched from forest to riverbed, and America needed tens of thousands of them. If you're enjoying this, take a second to subscribe. These are the stories that get forgotten, the infrastructure we take for granted. The scale of 19th century pile driving defies easy comprehension. Consider just the railroads. By 1860, the United States had over 30,000 miles of track. By 1880, over 90,000. By 1900, over 190,000 miles. Much of this ran through terrain that required bridges, rivers obviously, but also swamps, tidal marshlands, ravines, floodplains, any place where the ground was too soft or too wet for a simple earth embankment. A typical railroad bridge over a medium-sized river might have 10 piers. Each pier might require 150 to 200 piles, clustered together in a grid pattern and cut off level below the waterline. A concrete or stone cap would then be placed on top of the pile cluster to distribute the load from the bridge superstructure. That's 1,500 to 2,000 piles for a single bridge, and some bridges were much larger. The first Susquehanna River Railroad Bridge, completed in 1866, required over 6,000 piles. The original structure was a timber trestle nearly a mile long, on each bent supported by clusters of piles driven into the river bottom. 6,000 trees, cut and shaped and pounded into the mud. The earliest bridge across the Missouri River used nearly 8,000 piles. The bridge at Louisville over the Ohio River needed 7,000. When you add up all the railroad bridges built between 1840 and 1900, the number of piles driven reaches into the millions. Millions of tree trunks, pounded one at a time into American soil, by machines that worked 40 to 60 blows per hour, by men who had no safety equipment, no workers' compensation, no union representation, and often no legal protection of any kind. The bridges they built carried the trains that unified the country: cotton from the South, grain from the Midwest, iron ore from Minnesota, cattle from Texas, lumber from Michigan, coal from Pennsylvania. The economic integration of the American continent happened because goods could move by rail, and the rails crossed rivers on bridges built on wooden piles. Every shipment, every passenger, every piece of mail, every soldier moving to war, and every veteran coming home, all of it traveling over foundations that some nameless crew had hammered into a riverbed decades before. Not every pile went into a riverbed. Some of the most important pile driving happened on land that looked solid but wasn't. The problem was organic soil: swamps, bogs, drained lake beds, river deltas, coastal wetlands, places where the ground might support a man's weight but would slowly swallow anything heavier. Set a stone pier on this kind of soil, and it would sink. Not immediately, but inch by inch, year by year, until the structure above it cracked and failed. Chicago was built on this kind of ground. The entire city sat on a few feet of glacial, till over deep layers of soft clay. When the city tried to build heavy masonry buildings, they sank into the ground. Entire blocks had to be raised on jacks after construction. The streets were raised 10 feet or more, turning original ground floors into basements. Pile foundations solved this by reaching through the bad soil to something stable below. The piles acted like a forest of wooden stilts. Their combined friction against the soil, plus any bearing on hard ground at their tips, could support enormous loads. But determining how deep to drive was more art than science. Engineers couldn't see underground. They couldn't take soil samples the way modern geologists do. They couldn't run computer simulations of load distribution. They had to read the signs. The sound of the impact told them something. A pile driving through soft mud made a dull thud. One hitting clay rang differently. One reaching gravel or hardpan produced a sharp crack. Experienced pile drivers could estimate soil conditions purely from sound. The resistance told them more. Operators tracked how far each blow advanced the pile. A pile that was sinking 3 inches per blow was still in soft ground. One that had slowed to half an inch was hitting something. When it refused to go any further, even under repeated heavy blows, it had reached refusal. That was as deep as it would go. The concept of refusal became the key engineering metric. You didn't drive a pile to a specific depth, you drove it to refusal. This meant foundations automatically adapted to varying soil conditions. Where the ground was soft, piles went deep. Where it was firm, they stopped sooner. It also meant surprises. A pile that should have reached refusal at 30 feet might suddenly punch through a clay layer and start sinking again, or hit a boulder at 15 feet and refuse to go any deeper, leaving engineers to decide whether one short pile would compromise the whole foundation. These decisions were made in the field, by foremen with practical experience rather than theoretical training. They judged soil conditions by the color of the mud on the pile. They estimated load capacity by watching how the pile cluster settled under test loads. They were almost always right. The bridges they built lasted. Some of them are still standing. Here's a fact that surprises most people. Wooden piles, properly driven and constantly submerged, can last for centuries. Wood rots because of fungal activity. Fungi are living organisms. They need oxygen to survive. Underwater, below the water table, there's no oxygen. No oxygen means no fungi. No fungi means no rot. The Romans drove wooden piles to support the foundations of Venice around the 5th century. Some of those piles are still there, still solid, after 1,500 years. When engineers have pulled them for examination, the wood is often harder and denser than fresh timber. American bridges from the 1850s still stand on their original pile foundations. Engineers inspecting these old structures often find the wood in excellent condition. The piles are as sound today as the day they were driven. The key is constant submersion. A pile that gets exposed during low tide, or one that's driven through alternately wet and dry soil, will rot at the waterline. The zone of decay forms exactly where oxygen meets moisture. Below that zone, the wood stays sound. But the portions that stay permanently underwater essentially become preserved. The wood transforms over decades. Its cells become impregnated with minerals from the groundwater. Some old piles have essentially mineralized, turned to a substance more like stone than wood. This durability wasn't fully understood in the 1800s. Engineers knew that underwater piles lasted, but they didn't know exactly why. Some thought the wood somehow hardened through pressure. Others believed that river mud acted as a preservative. The science of fungal decay and oxygen requirements came later. Yeah, the practical knowledge came first. What they definitely knew was that pile foundations worked. They could be driven quickly with steam-powered equipment, they were cheaper than stone or iron alternatives, and they supported loads that would have seemed impossible just decades earlier. A well-designed pile cluster could support a stone pier weighing thousands of tons. That pier could support iron trusses weighing thousands more. And those trusses could carry trains loaded with freight, moving at speeds that would have astonished previous generations. All resting on tree trunks, hammered into mud, by steam-powered machines tended by immigrant laborers working 12 hours a day for $2 or less. The technology reached its peak in the 1870s and 1880s. By then, pile drivers had evolved into sophisticated machines with refined steam controls, improved hammer designs, and better rigging systems. The basic principle remained the same. Drop a heavy weight on a wooden stick until it won't go any further. But the execution had become more precise. Hammers could be fitted with caps to distribute impact force and prevent splitting. These were essentially heavy iron sleeves that sat on top of the pile and took the direct impact of the falling ram. The cap cushioned the blow slightly and spread the force across the entire pile head. Leaders, the frame guides that kept piles vertical, could be adjusted to drive at slight angles when needed. Some situations called for batter piles, driven at an angle to resist lateral forces. A bridge pier that would experience heavy current pressure might have some piles angled against the flow. Steam systems could be regulated to deliver consistent blow heights. Early pile drivers had simple on-off controls. By the 1880s, operators could adjust the lift height depending on soil conditions. A pile approaching refusal might need shorter, faster blows rather than the long drops used in soft ground. What had been crude in 1840 had become refined by 1880. And then gradually, the wooden pile began to lose ground. Iron and steel changed everything. The Bessemer process made steel cheap. Carnegie's mills made it abundant, and engineers began experimenting with metal alternatives to wooden piles. Cast iron piles appeared first, hollow cylinders that could be driven and then filled with concrete. They were heavier than wood, harder to handle, more expensive, but they could be driven deeper. They could carry heavier loads. They didn't need to be constantly submerged to resist corrosion. Steel followed, H-beams driven as piles, sheet piles for retaining walls, pipe piles for deep foundations. The strength-to-weight ratio of steel meant that a much smaller pile could carry the same load as a massive wooden timber. The first iron pile bridge appeared in the 1850s as an experiment. By the 1890s, they were becoming standard for major projects. The great bridges of the early 20th century rested on foundations that were fundamentally different from what pile drivers had pounded into riverbeds for 60 years. Concrete came next. Portland cement allowed engineers to pour massive footings in place. Cofferdams could hold back water while crews excavated to bedrock. Caissons could be sunk to depths that no wooden pile could reach. The wooden pile didn't disappear entirely. It remained standard for smaller bridges, temporary trestles, dock construction, and anywhere that cost mattered more than permanence. But for the great spans, the ones designed to last centuries, wood gave way to metal and stone. The steam pile driver evolved too. Diesel hammers replaced steam around the turn of the 20th century. Hydraulic systems replaced cable and pulley. Vibratory drivers could sink sheet piles in minutes. The lineage is clear. Today's pile driving equipment descends directly from those first steam-powered machines of the 1840s. But something was lost in the transition. Those early pile drivers were attended by armies of workers. Each machine required a crew of a dozen men or more. Each pile driven was a communal effort, coordinated by shouts and signals, accomplished by muscle as well as steam. Modern pile driving is largely automated. One operator in a climate-controlled cab can do the work that once required 20 laborers. It's more efficient, it's infinitely safer, and it produces no stories. Nobody will write the history of today's pile driving crews. There are no hardships to record, no deaths to mourn, no acts of endurance against impossible conditions. This is progress, unambiguously. Every life saved by modern safety standards is a victory. Every injury prevented by automation is a blessing. We should not romanticize the suffering of 19th century construction workers. They were not heroes choosing hardship. They were desperate men taking the only jobs available and dying because no one cared enough to protect them. But we can acknowledge what they did. We can remember that the infrastructure we inherited was paid for in blood as well as money. That every old bridge resting on wooden piles represents not just engineering, but sacrifice. The men who drove those piles didn't think of themselves as building a nation. They thought about their pay, about surviving the day, about getting home to families who depended on their wages. The grand sweep of history was invisible to them. They just drove piles. If you're getting something from this, subscribe. It makes these videos possible. Let me give you a sense of what that work meant in practice. A typical day started before dawn. The crew would arrive at the construction site while it was still dark. I'm stumbling over frozen ground or climbing aboard a barge by lantern light. The first task was always the boiler. Build up the fire, get the steam pressure rising. Nothing else could happen until that machine was ready. Boiler work was its own skill. You had to know how to lay the fire, how to adjust the dampers, how to read the pressure gauge. Too little pressure and the hammer wouldn't lift properly. Too much pressure and you risked a rupture. The steam boilers of that era were not precision instruments. They failed. They exploded. And the men tending them often died in the explosion. By first light, they needed to be working. The foreman would be watching. Every hour of delay was money lost. The contract likely included penalties for late completion. The first task was positioning. If the pile driver was on a barge, that meant adjusting anchors, checking moorings, verifying that the frame was directly over the next pile location. Survey stakes on the shore indicated where each pile needed to go. The barge crew would haul on anchor lines, moving the whole apparatus inches at a time until the pile driver frame aligned with the markers. If it was on land, that meant moving the whole apparatus along temporary tracks or rolling it on logs. 20 tons of machinery moving a few feet might take an hour of work with horses and levers and wooden rollers. Then came the pile itself. Workers would wrestle it out of a staging area, usually a floating raft of timber tied to the barge or a stack on the riverbank. They'd hook it to a winch, hoist it vertical, guide it into the leader frame. This could take 30 minutes for a heavy pile in difficult conditions. Everyone touching the pile was in danger. A slipping rope meant a falling timber. A shifting load could pin a man against the frame. A momentary loss of balance at the wrong moment was death. Once the pile was seated, the driving began. The operator would signal clear. Workers would step back, the steam valve would open, the hammer would rise, then the drop. That apocalyptic sound, the pile sinking a few inches, the hammer rising again. 40 blows an hour. Maybe 50 or 60 if everything worked perfectly. Each blow a small earthquake, each blow a test of every component in the machine. Chains that could snap, cables that could fray, steam connections that could rupture without warning. And between blows, workers would check the pile's position. Is it still vertical? Is it drifting off course? Is the impact cap properly seated? Has the pile head started to split? These checks required standing close to the pile while the hammer hung overhead. Trust in the operator, trust in the machine. Trust that the next blow wouldn't come until they were clear. Trust that wasn't always justified. By midday, they might have driven 5 or 6 piles, maybe more in good conditions, maybe fewer if they hit obstacles or had mechanical trouble. Lunch was eaten on site, often cold food brought from home. A tin pail with bread and meat, cold coffee in a bottle. There were no break rooms, no facilities, just the barge or the riverbank and whatever shelter men could improvise. The afternoon continued until darkness made work impossible. In summer, that might mean 12 or 14 hours of driving. In winter, perhaps 8 if they were lucky with the weather. But winter days were brutal in different ways. The cold, the ice, the darkness that came so early. Pay was by the day, not the hour. Every day of bad weather was a day without wages. Every day of mechanical breakdown was a day without wages. The men bore all the risk while the company reaped the rewards, week after week, month after month, until the bridge was done, or the job site moved, or the season ended, or the man himself was dead, or too broken to continue. Then pack everything up and relocate to the next crossing, the next river, the next 1,000 piles. This was how America built its bridges, not with grand visions or patriotic fervor, with exhausted men doing brutal work because they had no other options. I want you to hold that image in your mind the next time you cross a bridge, any bridge, but especially an old one, the kind with stone piers rising from the water, built before you were born. Under those piers, there may still be wooden piles, tree trunks that were standing in a forest before the Civil War, cut down in some timber operation we have no record of, stripped of bark by hands we cannot name, sharpened to a point by axes wielded by men whose faces are lost, floated to a construction site that no longer exists, hoisted vertical by ropes and rigging long since rotted, pounded into the riverbed by a machine that was scrapped 100 years ago, driven by operators who are buried in unmarked graves. Each pile represents a day's work, hours of effort by men whose names nobody recorded. Danger faced and survived, or danger faced and not survived. The friction of calloused hands on rope, the roar of steam and the crash of iron on wood, the bone-deep exhaustion of labor that never ends. 10,000 piles for a major bridge, 10,000 days, 10,000 stories we'll never know. But we know what those piles accomplished. We know they held. We know the bridges they supported carried the trains that built the American economy. We know that generations traveled over them, never thinking about what held them up. The steam pile driver was not a glamorous machine. It didn't inspire songs or monuments. It was loud, dangerous, dirty, and temporary. When a bridge was finished, the pile driver moved on to the next job or was scrapped for parts. Very few survive today. A handful in museums, a few more rusting in forgotten corners of old construction yards. The men who worked them are gone. Their children are gone. And even the grandchildren who might have heard stories are largely gone now. The oral history of pile driving has faded into silence, but the piles remain. Under the bridges we still use. Holding up the roads, we still travel. Sound after 150 years, keeping us safe on our passage, just as they were meant to. Every bridge of the railroad age, every trestle and span and crossing, exists because of these machines and the men who work them. The pile drivers made the foundations that made the bridges, that made the railroads, that made the nation, one blow at a time. If you made it this far, you're the reason I make these videos. Subscribe if you want to see more. I'll see you in the next one.